This section deals with the plasticity of the alveolar bone. As learning objectives, we want to address the structure of the alveolar bone. We want to get an understanding of the peridental bone remodeling processes, which are the basis for spontaneous and also for therapeutic tooth movements. And we also want to ask ourselves how static or how stable the dental occlusion really is against the background of these fundamental biological processes. Right at the beginning, not to forget that, the reference to my textbook Oral Structure and Biology. All anatomical basics that we address here in the context of this lecture are described in much more detail in that textbook. There I have laid down my knowledge of the last 30 years and also the latest research results up to that time. In a lecture, I can only touch them. I have also indicated the page numbers in the upper left corner for you to find the details better if you want to read in depth. So, the teeth are stuck in their alveolar bone in their bony compartments. Also in the jaw, we can distinguish between cortical and cancellous bone as in any bone. And around the roots, of course, the bone is very thin. We will see in a moment how little bone there really is. Before that, I would like to refer to the scanning electron microscopical image on the right. This is a snapshot. In that specimen, the bone appears so rigid and solid. You can see the cortical bone and the structure of the cancellous bone very well. But it will come out clearly, I hope, in the course of this chapter, that bone is by no means so rigid, but really plastic. In the end, from an orthodontic point of view, it is as soft as warm wax, if you want to have this analogy. And what this is due to, we will discuss in more detail later in the following. I still have my real skull here, which has accompanied me since my times as a student. The full body skeleton, which I also have, is made out of plastic, but this skull is real. And we can look at how the teeth are positioned in the bone. I can open this nice little door for you here. So, in this individual, the teeth are lined up nicely, so nowhere the teeth are in a crowded position or stand with an axial inclination. So the roots are also well in alignment and they are surrounded by the same amount of bone. If you have this anatomical picture in mind, then you can of course better understand any radiograph. However, the bone supply in the peridental region is actually quite poor and downright sparse. If you look at the sagittal schematic drawings, you can see how thin the bony lamella is around the incisors in the maxilla. To the nasal cavity, here labeled NC, there is still quite a lot of bone, but to the maxillary sinus, labeled MS for maxillary sinus, we see how little bone there is in the premolar and in the molar region. We will briefly look at the maxillary sinus in more detail later. And in the mandible, bone supply is not any better. Due to the lingual inclination of the molars, there's also little bone lingually, and there's actually always too little bone in the incisor region. In most of the cases, the roots of the incisors, with its enormously voluminous oral and vestibular extension, it is larger than the diameter of the symphysis, and often we see only a very thin bony lamella or even no bone covering the roots in the cone beam CT. The anatomist Bernhard Tillmann, from whose atlas these pictures are taken, shows very impressively the size of the marrow spaces in the mandible and the structure of the trabecula. It is astonishing to see how little bone there actually is. Here in the close-up picture we see the periradicular cortical bone and the interradicular cancellous bone. The cortical bone of the body of the mandible is of course impressively thick, and the bony enclosure of the inferior alveolar canal is also quite strong here. In this horizontal section through the molar region of the mandible, it looks something like a feeding trough, with the solid rims on either side and the cancellous bone holding the teeth in place. My favorite picture at the moment is the one on the right. Here you can see very nicely how the thin bony root cortex of this terminal molar is attached to the inner wall of the mandible with only very few trabecula. And on the far right of the picture again the inferior alveolar canal is visible. So this picture already shows that it does not take too much bone remodeling to set the teeth in motion. Nowadays, we apply the cone beam CT technology more and more in our diagnostics to evaluate the bony situation. In our adult orthodontic patients, where we do not know in detail how much bone there is available for the tooth movements that we have planned, we apply these cone beam CTs with good justification. From this, of course, we have learned a lot about bone anatomy for the benefit of all patients. The bone supply in the maxilla is also not really abundant, especially in the vestibular bone covering. Often, and especially today, when we do see more cone beam CTs of that region, we find much more fenestrations than we think is good. And in adult patients, where major tooth movements in the molar region are pending, we tend to apply cone beam CT imaging, as on the right picture, and there is also little bone there. Well, we know cone beam CT tends to show too little bone, but it is not much at all there. And that limits the possibilities of tooth movements considerably. The SureSmile software, which we use to overlay the optical intraoral scans with the cone beam CTs, reveals the bony deficit before an orthodontic treatment more than we would like. Against this background, I have been thinking about the goals of orthodontic treatment, and I'm convinced that we must not always primarily strive for an occlusion that meets the gnathological ideal, or that meets the 6 keys of occlusion as formulated by Lawrence Andrews. But we must also pay more attention to the bone surrounding the roots of the teeth. In the past, this diagnostics did not exist. It could not be seen in the 2D radiographs, and I do not know how many patients were treated with overstretched maxilla, but without any bone at the outer sides. And I do not know if we should be proud of a perfect 3-point occlusion if, to reach this, we have to uprighten the teeth so far for a maximum occlusal intercuspidation at the price that the roots then do not have a complete bony covering. Just in case you are ever faced with the question of how to shape the dental arch in which the teeth are crowded, this picture should remain in the memory of each of us, firstly, so that no one carries out an uncontrolled expansion of the dental arch with the danger that in the end many teeth are vestibularly completely without a bony coverage. And secondly, that we have to diagnose the individual bone supply for each patient before we move the teeth somewhere. And as far as the tooth axes and the occlusion are concerned, my first aim is to position the tooth axes in such a way that they no longer protrude from the bone as far as possible. With the maxilla, we have to make some effort since it is shaped like a pyramid. And if the molar cusps then still occlude with their mutual pits, and maybe with one contact point less than we have reached as a compromise, knowing about bone biology as well. I would like to put this up for discussion from the point of view of structural biology and orthodontics. If you still do not believe it, here again with a real skull. The bone covering here above the root of the first bicuspid is sometimes only as thin as parchment paper or completely open. The prevalence in young adults is about 1/3. In the view of the fact that we now know how little bone is actually present around the roots of the teeth, especially in the upper jaw, where the bone decreases upwards in a pyramid-like manner, when we see such tooth positions, we must assume that the roots are not covered by bone to a large extent. For me, the solution to resolve the crowding does not consist of simply widening the dental arch even more, as it is sometimes the case with a simple straight wire mechanics. This would lead to even much less bone around the roots with even more vestibular denudation. And it is even worse with these startup aligner stores that are not run by specialists and simply straighten the patient's teeth in the front and do not at all care about the bony conditions. So, what do we have to do to correct this crowding of the upper anteriors? We cannot just straighten the frontal arch. There's not enough bone there. Oh well, exactly. We have to distalize the posterior teeth. And this keeps them enclosed by bone and creates space for aligning the frontal arch segment properly. And this procedure is called sequential distalization. It works very well with aligner splints. You just have to make sure that the reciprocal forces are well controlled. We need a very good anchorage. We can do this here in the opposing jaw with elastics, or we can also use temporary anchoring screws. But that's too specific here. It's a lecture about bone. The expansion of the maxillary sinus and its close proximity to the molars poses a certain challenge for orthodontics. Here you can see two representations of the maxillary sinus, as they can also be found in our atlas, The Face. Carl Wesker has created these impressive images from the living. As a basis served a series of hundreds of MRI images of my daughter and of me. And in the right pictures, you can see the maxillary sinus of my daughter. At that time, she was still a student. And you can see in this young woman that there is still enough bone in the area between the molars and the maxillary sinus. We know, and we have to accept, that the sinuses in general expand more and more with age. And in the left picture, you can see the maxillary sinus of an older man. That is my maxillary sinus. It has already expanded around the roots of the teeth, and the root tips protrude deeply into the sinus. And in times when I catch a cold and when my maxillary sinus is also affected, I can feel it on the tips of the roots of the teeth, how it sloshes around in there. In any case, such situations with little bone, little cancellous bone, and very thin cortical bone are not any good conditions for orthodontically moving molars over long distances. If we want to understand why teeth move and why also we can move teeth orthodontically, we have to look at bone remodeling at the cellular level. In this series of images, to start with, we see here on the left a scanning electron micrograph of a bone surface which is crowded with cells. They are all busy, and in the histological image next to it, I can explain in more detail which cells are actively engaged in bone remodeling. In the histological section, the bone is shown here in the modified Masson-Goldner staining in blue, with isolated osteocytes lying within it. At the upper edge, the bone is surrounded by peridental fibers, and on the left there are sitting some bone lining cells to which they don't have any specific activity that we know about. But cells that really do something, those are the osteoblasts. They are sitting lined up on the bone surface and produce bone all the time. Also located on the bone surface are the osteoclasts. They are easy to recognize because of their size and the fact that they contain several nuclei. They are always located in their bone lacunae, which they have created themselves. For this purpose, they produce hydrochloric acid, and under the protection of a mucus insulation, which they also produce and secrete, they demineralize the bone in these places and reabsorb this mixture of calcium, phosphate, collagen, and the other matrix proteins, and then leave behind these rugged, chewed-up bony surface areas. In between, we can find always a few small osteoblasts. These then also quickly produce new bone, and so there is a balance between bone resorption and bone production, a steady state. But there are also regions in which bone deposition predominates and other regions in which bone resorption may predominate. With this sequence of images that we are about to see, I would like to emphasize once again the dynamics of bone remodeling. In the left image you see again the completely static scanning electron microscopical image of a piece of bone with the cortical and the cancellous bone. This colorful image shows a polychromatic sequence labeling technique. Using this method, you can show the dynamics of bone remodeling in animal experiments. So, let us say the green fluorescent dye was given into the food, or rather injected, on the first day, and during the next period, then the red fluorescent dye for another while, and then at last yellow. And then we see in the histological section, under the fluorescence microscopy, the excited parts of the fluorescent dye that have been incorporated into the bones. They shine so colorfully, so we see how different the distribution is over the time. At the bottom of the image, there is much more red than at the top, and yellow is not present at all the places. So we can conclude about the different shares of bone deposition at the times when the color staining was administered. Or here, these Haversian systems, the dynamics also becomes beautifully clear. What appears so static in the scanning electron microscopic image, these concentric bone lamella around the vessel perforation, becomes really alive in the image of the polychromatic sequence marking. Some Haversian systems remain in place and others are really migrating, so elongatedly distorted. If we now transfer what we have just seen to the tooth position, we can have a look at the tilting tooth in this diagram on the left. This tooth is tilting directly into the empty socket to its right. The center of rotation of the root is labeled in R, and then there are regions of traction labeled B, and pressure regions are labeled in C. The histological images show very impressively what happens in these different regions. These images were made by Andreas Jäger already at the end of the 1980s in the context of his investigations on bone remodeling in adolescents and in adults. At that time, we spent years together at Göttingen University in Germany doing basic research together. In this trichrome golden staining, the mature bone is stained turquoise and the fresh bone, the osteoid, is shown in red. And osteoblasts are located on the bone surface and fibroblasts are located in the periodontal ligament. And while the fibroblasts consistently produce desmodontal fibers, the osteoblasts accumulate bone, and the desmodontal fibers are immersed in the bone. And where the fibers run within the bone, which means when they are surrounded by bone, in this section, these fibers then are really called the Sharpey's fibers. Otherwise, they are not. In the right picture, we have the degradation side. Bone is again stained turquoise, and on the surface of the bone there are the osteoclasts, large, multinucleated, amoeboid motiles sitting in the bone lacuna. And in the immediate vicinity, there is a voluminous vein into which the osteoclasts transfer a part of the calcium and phosphate they have just extracted. And that way, it's not lost to the body during this bone remodeling process. These are the cellular processes that contribute to the dynamics of the alveolar bone. Today we know more about bone remodeling behavior at the molecular biological level. With these schematic drawings, I would like to prepare you for a future that you will definitely have to deal with when it comes to intervening with drugs into the molecular mechanisms of the regulatory circuits. For therapeutic reasons, we might want to promote bone formation or accelerate bone resorption at certain points during tooth movement. So, there is so much detailed knowledge that a single person can hardly keep track of. In this lecture, I would like to give you at least only a small insight, so that you might read yourself further into the literature. When you do it, you will know what it is all about. So, when force is applied to a tooth, that can be pressure from the soft tissues or also from orthodontic appliances. It can also be undesirable effects when bridge restorations for some reasons create forces, have lever arms and torques. So the bone notices that. And the forces are sensed by the cells through mechanotransduction. And there's also a lot of molecular messengers around. So when there is traction on the desmodontal fibers, cytokines and growth factors are released by the cells that perceive the traction. In the process, the osteoblasts and fibroblasts, which are all mechanically connected to the fibers, also regulate the genetic activity, the expression of vascular endothelial growth factor, VEGF. And if the concentration of this increases, then the pericytes in the blood vessels and the pluripotent stem cells in the mesenchyme and in the bone marrow, they also notice this, and pre-osteoblasts are formed from them, which are subject to control by the transforming growth factor TGF-beta and the insulin-like growth factor IGF-1. These two growth factors also regulate collagen synthesis and fiber formation, but in the end, new osteoblasts have now been formed, which form osteoid, pink on the left in the picture, and then finally bone, which is shown in gray. So I find this very difficult to remember these artificial biochemical names and the abbreviations, but we have to know them. One day it will be quite normal for us to intervene biochemically. We can see that the receptors I marked on the osteoblasts and the red triangle symbolize specific proteins, which means messengers and growth factors that regulate the activities of the cells. Let us also address the resorption of bone. Here the trigger is a compression, a force on the tooth-supporting tissue and on the bone. This is also perceived by the fibroblasts and the many other cells that are present there in abundance. They then release prostaglandin E2, interleukins and tumor necrosis factor alpha, which stimulates the osteoblast to produce chemokines. This is a certain detour to bone resorption because only these chemokines and tumor necrosis factor alpha, which have just been produced by the osteoblasts, together with RANK. This is an abbreviation that stands for Receptor Activator of Nuclear Factor Kappa Light Chain Enhancer. So, if you don't understand anything here, this is just a word of its own. I just want to open the door a crack wide for you. So, via this roundabout way, the osteoblasts release all these molecular signals. Osteoclast precursors are formed from monocytes, which are abundant as stem cells in the bone marrow. And several of these osteoclast precursor cells then fuse to form the multinucleated osteoclasts. These osteoclasts carry a lot of receptors on their cell surface by which their activity is controlled. With all these control molecules, it is now clear that it is possible to intervene with drugs. For example, the production of osteoclasts can be inhibited by inhibiting the important RANK with osteoprotegerin. Bisphosphonates are already used therapeutically to inhibit bone resorption. However, they have considerable side effects which we do not need to discuss here, but which you need to know in detail for your work with patients. Let us have another quick look at the osteoclast schematically, but very much close up in this picture. In the upper right corner, I have drawn some receptors, which actually protrude from the cell membrane as spatial protein structures, and if a suitable signal protein docks on, then this is passed on to the cell membrane as information, which is biochemically but also electrically or even mechanically passed on through the cell plasma to the cell nucleus. The cell nucleus, an osteoclast has several of them, so then they can react to it and change their metabolism. For example, they secrete protons that generate hydrochloric acid with a pH of 4.5, which enables them to dissolve bone. In addition, then, they secrete a mucus so that the hydrochloric acid cannot flow around the whole area. So now you have a rough idea of what is going on with bone resorption. And by the way, this happens with each of us everywhere at the bone, also right now, while you're listening to this lecture. Not that you are completely confused, but of course one has to look at the bone and resorption processes and the bone deposition processes together and not in separate schemes. We have also seen osteoblasts and osteoclasts lying next to each other on the histological sections. So they really do influence each other. All right, but this is now expert knowledge. I just wanted to point it out for you. If you need to, you can read it up. It took me 2 weeks to create this scheme until everything did fit together, and hopefully it is still correct today. To conclude this molecular section, I would like to remind you of The Sorcerer's Apprentice by Johann Wolfgang von Goethe. Most of you must have had to learn it by heart in school. Now it has its meaning. Old Goethe already knew. I cannot get rid of the ghosts I called. I mean, if you want to intervene molecularly in the bone metabolism, you can only do so if you know exactly what you are doing, which means if you know exactly what's going on the molecular level. And otherwise, it can end in a catastrophe, as Goethe already described with The Sorcerer's Apprentice. Now it becomes more visual again. With all what we know, what happens in the interface between the tooth and the bone, it is not surprising if we ask ourselves whether the teeth are static and firmly attached to the bone, or maybe not. Well, many laymen think they are. Also our patients in orthodontics, who always neglect the retention measures until they themselves notice a relapse of a malalignment of their teeth. So here you see the teeth are consistently moving forward. This mesial drift is, out of many reasons, probably due to the fiber contraction. So I can imagine that all the retaining fibers run all around, intertwined, and they not only run from tooth to the bony socket, but also do they run from tooth to tooth, and they run in figure-8 tours along the entire dental arch. And when this conglomerate of fibers contracts, it can pull all the teeth together mesially over time, which may last for years. And of course, this is then associated with bone remodeling. In any case, the teeth are not stable at all. They rock like the ships in a harbor. And here you see the sailing ships in the harbor of Embarcadero in San Francisco. The ships there are tied well. They cannot leave, but they rock back and forth. There is even morphological evidence that the teeth also rock in this way. In the cementum, in the histological picture on the left, labeled B, we see vertical lines. And in the diagram next to it, labeled C, I have exaggerated these lines. And within them, then there run these sharp-based fibers. And here they can really be called sharp-based fibers because by definition, they are surrounded by hard tissue. So these fibers change their direction in each layer. It is just like when the harbor worker always throws a ladle of cement at the ship's ropes, and while the ship is rocking so that the current angle of the rope is immediately fixed in the cement. And if it changes its direction, immediately another layer of cement is added. So we have the histological proof that the teeth rock like the ships in the harbor. And if you make a scan of your teeth every week, then after a year you will also have a jerking cartoon of your teeth, like the rocking ships in the harbor. So what forces can act on the teeth? Where do these forces come from? This can already be the lips, the tongue, all the soft tissues. And if we zoom in higher here, then we come back to the histology in the periodontal tissue. Here on the left in the histological vertical section, we first see these layered light and dark zones at the alveolar crest. These are the reversal lines described by Donald Enlow. This is where alternatively bone resorption and bone deposition take place. And the stronger mineralization is seen as particularly dark colored lines. So the bone marrow spaces are very much filled with fat, which is an indication that this specimen comes from a quite old individual. And the connection between the bone marrow canal and the periodontal gap can also be seen nicely in this section. And as everything is fluid in here, so you can easily imagine how the hydraulically supported teeth and the periodontal gap are not only held in place by the fibers, but also by that fluid. And tooth displacements also lead to an in and out of the fluid through the bone marrow spaces connected to the periodontal gap. And here is another higher magnification from the same section. You can see how the periodontal fibers run obliquely from top to bottom, with a thick blood vessel at the top and this connection to the bone marrow spaces and connection with the alveolar bone at the bottom. And quickly back to the patient. We have, of course, orthodontically treated the crowding of the teeth. It is important that there is as much bone as possible between the roots. Where the teeth are too close together, the roots are also too close together, with little space for bone in between. So if bone loss occurs one day later, then it is especially likely to occur here, where there is already too little bone. So it is a prophylactic measure to secure the bone and to keep the teeth on the long run. If the teeth are positioned evenly in the bone in good time, this ensures better that they remain there and do not migrate any further. And therefore, this is why we glue in this retention wire, and the patients are given another splint over the dental arches, removable, for once a week, but for life. Let us come back to the research on bone remodeling I was able to do together with Andreas Jäger many years ago. At that time, we also once, but only once, we also treated rats orthodontically. The histological section shows a molar with its roots surrounded by bone. And here on the left, the bone surface is smooth. That is the traction zone. And opposite, the bone surface is jaggedly pitted like this, and this is the work of the osteoclasts in the pressure zone of the tooth movement. So the tooth is moving to the right. We also marked the bone deposition with fluorescent dyes. You can see very nicely the bone deposition in the traction zone. It glows really bright green, but it took me a while then to understand why it also glows green at the breakdown zone. I expected the result to be much more schematic, but it is clear that there are also osteoblasts in the pressure zone, in which bone is primarily degraded, and that is why it is still glowing there. But that is new bone, which will then soon be eaten away again by the osteoclasts. And the cement is also constantly built up, so it also glows a little bit. In reality, the layers are much thinner than the shiny glow, but the shiny glow may have led to some overexposure on the film in the camera at that time. So in the histological sections, you can see the comparison, the zone of bone apposition and the traction zone in the left image, and the pressure zone with the jagged bone resorption in the right image. And here you can even see some resorption lacuna in the cement. There, some osteoclasts have managed to migrate the 250 micrometers that such a periodontal gap is thick from the bone to the cement and continue eating there. Then they are called cementoclasts, do essentially the same thing there. And the tooth then moves to the right. An important topic that interested Andreas Jäger at that time, and of course also me, was the question of whether adult patients can be treated orthodontically just like we treat adolescent patients. You have to know that in the last century, far fewer adult patients were treated than we do today. Today, more than 50% of my orthodontic patients are adults. But people used to think that orthodontics was only for children. That's not true. Teeth move throughout life and facial growth never stops completely. So the question was at that time, what kind of differences in the physiology and the cell population in the alveolar bone do we expect when we compare adolescents with adults? What is different in bone to begin with? And in the young bone, the bone trabecula are still thick. The bone marrow spaces between them are present, but the meshwork of the trabecula makes the impression to be stable. The bone volume is still quite high. And in the older person, in the right picture, the bone mass has decreased significantly and the trabecula are thinner and also more sparse. The bone marrow spaces, on the other hand, have increased significantly. And a similar observation is made in the bones of astronauts in space in zero gravity, and also to you if you are just sitting there quietly in front of the computer screen and allow little musculoskeletal stimuli to act on your body. This was also currently studied impressively in Berlin in the context of space medicine. The findings are similar to those shown here in the pictures. So, now here are the histological sections of the traction zone on the left and the compression zone on the right. This is the condition in a young person. In the left image you can see very nicely the osteoblasts, the freshly formed bone, all in red, and the fibroblasts, the fibers, and all very numerous in the young person. And on the bone resorption side, the osteoclasts are active, just degrading bone. The resorption lacuna are well populated with osteoclasts. The tooth that would be located between the two histological images, that tooth that would move from left to the right. And now here is the situation in the elderly person. Basically the same, but the scene looks very much abandoned. We see there is also a layer of newly formed bone in the left picture, nice and red, but only very few cells are visible. The fibers are also very sparse. This is also known from the hair on the head, which becomes less with age. And in the right picture, the resorption zone. There are resorption lacuna visible, but some are even abandoned, so there are also fewer osteoclasts around. And the tooth, as before, would move to the right. If we now want to treat an adult patient orthodontically, then it is clear from these images that this should work. All the necessary cells and the tissues are present, just fewer cells and less tissue. But when we start the treatment, we first have to work with much lower forces in the older patient for a longer period of time. This means with smaller steps in case of sequential aligners, and with thinner elastic arch wires for a longer period of time in the case of multi-bracket systems. And during this time, the cells have the opportunity to ramp up their activity and to multiply in number. When they are all active, then they are just as active as in a young person. And in the end, treatment of an adult patient usually takes only a year or a little longer, simply because there is less bone for the teeth to pass through. At the end of this lecture, I would like to show you a patient case. That was my first adult patient whom I got to see as a young resident in orthodontics, whom I then treated under supervision. The face is characterized by a prominent lip step, and intraorally the dentition does not look very favorable. The upper anterior teeth are very much protruded with spaces, and the lower anterior group is biting into the palatal marginal gingiva, a periodontal traumatic situation. And the lower lip is being sucked into the enlarged sagittal overjet. The occlusal view on the picture on the right shows the protrusion and the spaces, and also a lot of calculus. This was a time before the general introduction of periodontal prophylactic care, which is today taken for granted every 6 months. Dental care in terms of prosthetics was good. The bridge, porcelain fused to metal with physiologically correct occlusal contacts, was high standard at that time. And with this imposing enlarged overjet, and because it is an adult patient, we first of all assumed it could be a surgical case. The lateral head film also shows the extremely impressive overjet. But the cephalogram on the right, here just quickly the A and B angle, shows that the skeletal bases, which means the maxilla and the mandible, are well in alignment. It is not a surgical case, but it's a purely dental problem. The anterior teeth in the maxilla are extremely much protruded, and this is why the overjet is so impressively large. Let me cut this a little short. We made a setup in the plaster cast as a trial, and even if we closed the interdental gaps completely, the overjet would have not been eliminated completely. But it was our goal to achieve a physiologically correct relation of the incisor groups. So we had to extract a bicuspid, the 2-4 or the 12 in the US numbering system. On the patient's right side, in the picture it was on the left, we could not extract the first bicuspid, so the pontic had to be removed. And now the situation was also asymmetrical, which is always a bit more complicated. And in the right picture you can see the spaces in the region of the first molars. The second and the third molars are clearly angulated mesially, and now that you know the histology, this should no longer surprise you. In terms of treatment technique, it is now important to move the anterior tooth group in the upper jaw backwards in such a way that it is not tilted, which means not with the crowns backwards first. Instead, the teeth must be guided so that the roots come backwards first and only then the crowns follow. So a torque must be created and well controlled that moves the teeth backward with the roots first. To that end, we have bent a T-loop like this with calculated and individually activated, and the gap closure is then created by opening the legs of the loop. To do this, the arch wire is pulled distally and thus activating the loop. So I do not want to go into too much into detail about the multi-bracket technique, but you see, you have to be very precise biomechanically here for biological reasons. Otherwise, the root tips will protrude and stick out of the bone in front. So in principle, we still do it like that today. However, the brackets are only a quarter of the size nowadays. The occlusal view shows nicely how the anterior group has come together, and the gaps are already mostly closed in the frontal region. Anchoring is done at the back with a palatal arch and with a headgear. We no longer use a headgear today. Today, we would also place an anchoring implant there, but that was not common at that time. In here, all the spaces are now closed, the bridge in the upper arch renewed, and new bridges have also been inserted in the lower jaw on either side. And the lateral head film shows that we have changed almost nothing skeletally. It was mainly a matter of correcting the position of the front teeth. Treatment time was 1 year and 8 months. Today, it would perhaps be a quarter of a year faster, but ultimately biology dictates the speed. Bone remodeling takes time. Before I show you how much bone has been remodeled in this way, I first want to show you the effect on the patient. The exterior of her face has improved significantly, which I think I do not really have to comment. On the right, the intraoral situation. The anterior teeth are now in good position. I would have liked to see a better occlusion and a better interdigitation on that bridge work, so that could have been designed in a better way. Anyway, so now we can compare the initial findings and the results in the plaster model, which I cut in half for that purpose. It is the volume of a thimble or a cherry that we have remodeled here through orthodontic treatment. That is what I wanted to show you with this patient case and with this lecture. Bone is so plastic, also therapeutically, and in relatively short time, that is a pretty big volume that we have changed here. And these are cellular achievements that we have initiated here. As a take-home message, we can now summarize and state that we have taken a closer look at the structure of the alveolar bone and that the availability, or the bone volume, is quite scarce. Bone remodeling is taking place continuously, which ultimately means that the tooth position is not stable at all. This also has an impact on the stability of the occlusion, and for biological reasons, patients must be monitored throughout their lives in dentistry and in orthodontics to ensure stability of tooth position and functionality of the chewing organ. And with this picture of my horse Poseidon, I thank you for your kind attention.